So, okay, let's start the next session. And then we welcome Claudia D'Amato, that works at the University of Bari, and that will sum up for us 10 years of machine learning for the semantic web. So, Claudia, if you can share your screen.
Yes.
Yeah, perfect.
Okay.
And then.
Good afternoon, everyone, and many thanks for your invitation to this conference. I work for the University of Bari, which is in the south of Italy, and I work, mainly my work is on developing machine learning methods for the semantic web since several years. And today I'm going to present some of my lessons learned along these years, and most of all, my envision next challenges. The machine learning goal, the semantic web goal is to make the data on the web machine understandable, and in this regard ontologies play a key role since they act as a shared vocabulary for assigning data semantics, and because of that a lot of effort has been put on developing real ontologies that could be actually used, and some examples are the schema.org, the Gene ontology, the FIBO ontologies, just for making a few examples. Interestingly, ontologies are equipped with deductive reasoning capabilities, which allow to make explicit the knowledge which is implicit within the ontologies. So looking at this picture where we have a rough idea of an ontology, where we have a concept, bank, company, and person, and we know that a bank gives credit to person, and that a bank is subconcept of, or subclass also so told, of the concept company, we may infer deductively speaking that Crédit du Nord and Crédit Agricole are also instances of the concept company, besides of being instances of the concept bank, and this is mostly due to the subclass of relationship existing between these two. A lot of effort has been also put in making the vision of the web of data actually real. That means in in creating a global scale interlinking ontologies and data. And in this regard, initiatives such as the linked data that represents rules for making easier and easier publishing, linking, and sharing data on the web can be recalled, and the linked open initiatives that pushed a lot on having public and open larger and larger data set. And in this regard, DBpedia act as a driving force for developing the giant linked open data cloud. Nowadays, we are facing the era of the knowledge graphs, and indeed we can find several existing knowledge graphs actually available, both as an open knowledge graph, that means with content freely available, and we can cite, just for making a few examples, BabelNet, DBpedia, Freebase, Wikipedia, or Iago, but we can also find several examples or enterprise knowledge graphs that have been developed for commercial usage by industrial giants. And here we can cite Google, Amazon, Facebook, LinkedIn, Microsoft, AstraZeneca, and actually many others can be listed. Knowledge graphs are actually widely used in several applications, such as e-commerce, semantic search, fact-checking, medical decision support system, question answering, and machine translation, for making a few examples. But they are also the subject of study of several research fields, such as information extraction, natural language processing, machine learning, knowledge representation, the web, robotics, and others can be cited as well. Despite of the fact that knowledge graphs are quite widely used and adopted, for the best of my knowledge, there's no actual consensus of what a knowledge graph is. Here, I'm going to adopt the definition of knowledge graph provided by Hogan and colleague, for which a knowledge graph is actually a graph of data intended to convey knowledge of the real world and conforming to a graph-based data models. Here, nodes represent entities of interest, and edges represent different relationships that occur between these entities. Also, a knowledge graph can be enhanced with schema-level information, and in this regard, ontologies are quite often employed to define and reason about the semantics of the node and edges. And standard representation languages that have been developed in the semantic web, such as RDF, RDFS, and DAO, are quite largely adopted. And because of this motivation, knowledge graphs are generally grounded on the open world assumption. A key feature is that knowledge graphs are actually very, very large data collection. As such, a knowledge graph, the knowledge graph that will be considered will be a collection of statements that are triples of kind subject, predicate, and object, where the subject and the object are resources in our knowledge graph, and there exists a predicate that means a relationship between the subject and the predicate. And we may also find that some resources can have some formal definition in existing ontologies, such as, for instance, a definition for science fiction movie. In these complex scenarios, of course, issues may arise. For instance, it is quite well known that knowledge graphs suffer of incompleteness and noise because they often come as a result of a complex building process. And because of that, we may find that some links are missing, or on the other hand, there are some links that have been reported within the knowledge graph, but they are actually wrong with respect to the domain of reference. Additionally, we may also have ontologies and assertion that can be out of sync, thus resulting in incomplete modeling of the word, or these can provoke some noise within the description of the word, or sometimes the wrong usage of ontologies as a vocabularies and the assertion may also create some inconsistencies within the ontology. And when we have inconsistent ontology, we cannot perform any kind of reasoning, I mean deductive reasoning, and also noise within the data may also generate counterintuitive results when we try to reason on top of that. In order to face some of these problems, machine learning methods have been quite largely adopted with the idea of discovering new and additional knowledge by exploiting the evidence coming from the data. And in this regard, both symbol-based methods and numeric-based methods have been actually developed. At the beginning, symbol-based learning methods have been mostly used for targeting ontology mining related tasks. And for ontology mining here, we refer to all those activities that allow for discovering hidden knowledge from ontological knowledge bases. And the key point of this method is that they are able to exploit the background knowledge which is provided by the adopted ontologies, and also deductive reasoning capabilities may be integrated within them. So we mostly with symbol-based learning methods, we exploit an inductive approach, but which is integrated with deductive reasoning capabilities as well as the existing background knowledge. Several interesting results have been registered, but in terms of scalability, when we think about the dimension of the existing knowledge graph, they still result limited in the ability to scale on the whole knowledge graph. which motivated mostly the interest in the last few years with respect to the adoption of numeric-based learning methods, mostly for targeting knowledge graph refinement tasks, and specifically link prediction and triple classification are gaining most of the attention, where link prediction aims at predicting missing links between entities, whilst triple classification aims at assessing if a given statement that is a triple subject, predicate, and object, which is within a knowledge graph, is actually correct or not. And the main motivation of this attention is given by the ability of these methods, these numeric-based methods, to scale on the very large knowledge graph. But on the other hand, these methods actually disregard any schema-level information and reasoning capabilities. The other problem with the numeric-based learning methods is that they mostly consist of a series of numbers without any obvious human interpretation. And this would be a problem in some domains, such as the drug domain, where we would like to predict the side effect of a given compound, but most of all, we would like to understand somehow the motivation of this prediction. And this is something that cannot be found with, cannot be part of the products, let's say, that is provided with numeric-based learning methods, thus limiting the ability of understanding the motivation of some predictions. And in some domains, this would mean to somehow compromise the trustworthiness of the results. On the other hand, in this regard, symbol-based learning methods should be most appropriate, because they most of the time provide interpretable models that are able to generalize conclusions. We can think about the generation of trees or rules or logical formulas that can be somehow exploited for a better understanding of the provided results. It has also been proved that it is possible to integrate and to combine these symbol-based learning methods with deductive reasoning capabilities to make prediction and to improve the quality of the prediction. But as I said before, despite of the effort of improving the ability of this method to scale, and indeed several results have been registered in this regard, still they cannot be directly applied to a whole knowledge graph. So what I will try to do in the rest of this talk is to try to provide results to a couple of questions. The first one regards numeric-based learning methods that almost disregard background knowledge, the existence of background knowledge, and the exploitation of deductive reasoning capabilities. And the first question would be if it is possible to somehow enhance these methods with the schema-level information and deductive reasoning capabilities, and try to understand if this could be actually beneficial. The second question that I'll try to address if it is still possible to think about applying symbol-based learning methods given the dimension of the knowledge graph, and why we should do that. What are the benefits of doing that? I will start with the first, let's say, the first question concerning numeric-based learning methods, and particularly I focus on knowledge graph embedding methods, because among the different numeric-based learning methods, this class of methods showed an impressive ability to scale on very large knowledge graph. Knowledge graph embedding methods mostly convert a data graph into an optimal low-dimensional space, where somehow performing knowledge graph refinement task is, let's say, easier. And this conversion is made in a way that graph structural information are preserved as much as possible. These methods, despite of the fact that knowledge graphs are grounded on the open world assumption, at the opposite, are generally grounded on the adoption or of the closed word assumption or the local closed word assumption. Additionally, as I already mentioned before, this class of methods generally disregard schema level information and reasoning capabilities. There is a plethora of knowledge graph embedding methods around, and they can be somehow categorized along three different dimensions. One is the representation space that could be pointwise or complete or complex or discrete or Gaussian manifolds and other representation space that could be actually mentioned. The other dimension is the encoding model that could be linear factorization, neural models, and other encoding models more complex encoding model could be cited. And the third dimension is the score function, which is adopted, which can be grounded on a notion of distance or energy or a notion of semantic matching, or also other criteria have been adopted. All in all, the architecture of the knowledge graph embedding methods is depicted here in this slide. And the goal of knowledge graph embedding methods is to learn embeddings that are vectorial representation of the initial graph, such that the score of positive triples, also called valid triple, is higher than the score which is assigned to negative triples, also called invalid triples. And this problem is solved as an optimization problem, specifically by minimizing a loss function, which is ultimately grounded on the score value, which is assigned to the positive and negative triples. Here, the main point and the presence of negative triples is actually necessary for training this kind of models. Here, the main problem arises because actually negative triples can be hardly found in knowledge graphs. But since these methods definitely need negative triples, negative examples in order to learn these methods, to train these methods and predict ultimately predict the results, the way in which negative triples are generally generated is by the use of a random corruption process. That means that given a triple, either the subject or the object is replaced with another individual, another resources, which is present within the knowledge graph. As you may easily understand, in this way, you can easily generate a bunch of false negative examples. So from here, the idea is to try to enhance existing knowledge graph embedding methods by injecting the background knowledge within them somehow, and also by exploiting reasoning capabilities. And this is actually done by developing two different components. The first component is developed for building up an informed way for generating the negative examples, particularly by exploiting domains that are already present in the background knowledge, axioms that are already present in the background knowledge, and these are domain, range, and disjoint with and the functional property axioms, and by exploiting a suitable reasoner with the final goal of limiting the number of false negative examples that can be generated. The second component inject the background knowledge within the loss function, actually guiding the way in which the embedding vectors are learned by, again, exploiting axioms that are already available within the background knowledge. And specifically, we focus on equivalent class, equivalent property, inverse of, and subclass of axiom. For completeness, it is important to say that other methods have been developed trying to inject the background knowledge within within knowledge graph embedding methods. The main point is that these models actually exploit additional sources of information for training the knowledge graph embeddings methods, such as data log clauses or logical rules. So as such, they are not directly applicable to an existing knowledge graph, because additional source of knowledge are required. Here, I'm going to present an approach for learning embedding vector embeddings while exploiting the background knowledge. And specifically, I illustrate TransAul, which is grounded on TransE, and TransRAul with jointly with its variants, which is named TransRAul-R, which is grounded on TransR. It is important to highlight that this framework somehow can be applied to more complex knowledge graph embedding methods, but it requires additional formalization if more complex embedding methods are taken into account. So let's start with the TransAul, which uses TransE as a base model. Indeed, it maintains the very same setting adopted by TransE, which learns the vector embeddings by minimizing margin-based loss function, which, as I said before, ultimately is grounded on the score, which are assigned to positive and negative triples, where the negative triples are those represented by this delta prime set of triples. And the score function is actually grounded on a notion of similarity of the translated subject embedding with respect to the object embedding. What TransAul does is to use the very same loss function adopted by TransE, but it generates additional triples considering the existing information within the background knowledge, where this existing information is provided by the exploitation of the equivalent class, equivalent property, inverse of, and subclass of axioms. Because of these additional triples that are actually generated by exploiting these axioms, the loss function is made slightly more complex in order to take into account these additional triples. So as you can see here, we have the loss function adopted by TransAul is the very same loss function adopted by TransE with the addition of different components, each one represented the bunch of triples that are generated with respect to the corresponding axiom that has been considered. So this component stands for the loss function that need to be computed when triples coming from considering the inverse of axioms are taken into account. The same for the equivalent property axiom, for the equivalent class and subclass of axioms. We moved on with this setting from TransAul to TransRAul for two different reasons. The first one is to show the generality of the approach. That means we can change the base embedding models, which for TransAul is TransE, and it is still possible to apply the way in which the knowledge graph, the background knowledge is injected within the knowledge graph embedding methods. The second motivation is that it is quite well known that TransE is poor in modeling reflective and non-one-to-one relationship, which is, for instance, the case of the type of relationship where we have one individual that could be instance of several concepts, and a concept or class can have several instances. In this regard, TransAul resulted more suitable to handle such kind of specificity. So what we do with TransAul is to replace TransE with TransR. The first thing that we need to do is to understand what are the main differences between Trans-Z and Trans-R. Trans-R actually adopted the very same loss function adopted by Trans-Z, but a different scoring function, which is again grounded on a notion of similarity, but the score function adopted by Trans-R preliminary project the embedding vector of the subject and the object into a different embedding space with respect to the one of the vector embedding the relationship, and the two spaces are put together by the use of a suitable projection matrices, which is this ham depicted here. So if we would like to use the very same approach that has been exploited for Trans-R, but adopting a different base model, which is Trans-R in this case, the only thing that we need to know is, given the general formulation of the loss function that we have just seen for Trans-R, to replace the score function of the base model, which is now the score function of Trans-R rather than the score function of Trans-Z. In this formulation, we have also added some weighting parameters that are these lambda 1, lambda 2, lambda 3, lambda 4, whose role is to weight the influence that each function term may have during the learning phase. Of course, if we put the value of these lambda parameters equal to 1, we have the very same formulation of Trans-R, apart from the fact that a different score function, which is the one adopted by Trans-R, is adopted in this case. We further moved from Trans-R to Trans-R because we tested a different way for exploiting and for injecting the background knowledge. The second approach that we adopted is an axiom-based regularization approach that, differently from the approach used by Trans-R and Trans-R-OWL, that explicitly generate new triples that are taken into account when computing the loss function, the axiom-based regularization approach does not generate additional triples, rather add specific constraint directly to the loss function. This approach has been proposed by Minervini and colleague in the model dubbed Trans-Z-R, which is grounded on Trans-Z, and as such, the score function is exactly the same adopted by Trans-Z, but the loss function has been modified by adding, besides of the score function of, the loss function of Trans-Z, by adding suitable axiom-based regularization for only two axioms that are inverse of axiom and equivalent property axiom. In order to exploit, to adopt this approach for the case of Trans-R, we need to apply some changes. The first one is that we need to adopt the score function adopted by Trans-R rather than the score function adopted by Trans-Z, and this is quite straightforward. The other changes that we need to apply is that besides of inverse of and equivalent property, we also consider additional axioms that are equivalent class and subclass of axioms that need to be injected within the background knowledge with suitable regularizers. And this is what happened here with this regularizer for the equivalent property and this other regularizer for the equivalent class. Even more so, we need to take into account that Trans-R adopt a projection matrices for putting together the two different spaces in which the resources and the relationship are mapped in the different vector spaces. That means we need to take into account that a projection matrix is considered. That's why an additional term has been added for the case of the inverse of and equivalent property axioms, which is added in order to favor the equality of the projection matrices, thus preserving the semantics of the inverse of and the equivalent property axioms. What we have done is to assess the fact if exploiting background knowledge and reasoning capabilities would be actually beneficial. And in this regard, we compared Transar-Owl, Transar-Owl, and Transar-Owler with respect to the baseline models that are Trans-E and Transar. We tested these models of performing a number of link prediction and tripole classification tasks that have been adopted by tested by adopting standard metrics. As knowledge graph, we considered knowledge graph publicly available, and among the others, we picked NEL on purpose because this would serve as a sort of stress test for our models. And why this was a stress test for our models? Because actually NEL lack of some of the axioms that are actually considered by the developed models. Indeed, NEL does not have equivalent class and equivalent property axiom, has a very limited number of type of triples, but it has an abundance of subclass of triples. So the idea here was to test if the abundance of the subclass of triples could somehow compensate the absence of the other axioms. And what we found out with our experiments is that Transar-Owl and Transar-Owler were actually able to outperform the baseline models in most of the cases, particularly looking at the comparison between Transar-Owl and Transar-Owler, which was important in order to understand which of the two approaches either generated additional triples explicitly, which is slightly more costly, or adopting an axiom-based regularization approach would be the most appropriate one, the one providing better results. We found out that Transar-Owl, which is the one that explicitly add new triples, is registered slightly superior performances with respect to Transar-Owl-R, which is the one that adopts an axiom-based regularization approach. So somehow confirming our initial intuition, our initial idea. Things were slightly different in terms of the results for the case of NEL that was aimed as a stress test for our models. And indeed, in this case, the developed models registered oscillating performances with respect to the baseline, showing that more robust models need to be developed when missing information, specifically missing axioms, can be found within the considered knowledge graph, which motivated actually the idea of further enhancing the developed model by exploiting a more fine-grained representation of the semantics of the relationship. This more fine-grained representation of the semantic of the relationship has been proposed by Zhang and colleague and formalized as a three-level hierarchical structures, where at the top of the hierarchical structure, as a root node, we have clusters of relationship. At the middle level of the hierarchical structure, we find the actual relationship, and as a leaf node, we find sub-relationship that are actually different nuances with respect to a notion of context of the very same relationship. What we have done is to integrate this model in the models that have knowledge in the enhanced knowledge graph embedding models that have been developed, and this has been formalized in this way. First of all, we need to provide a formalization, actually following the proposition by Zhang and colleague. First of all, we need to provide a formalization for the loss function, which is the one that is adopted for solving the optimization problem. And the loss function is actually given by the summation of two different components. The first one is the loss function of the base model, which for our case was transr owl, or its variant transr owl. The second component is the loss function, which is computed by considering the hierarchical relational structures. And here we need to consider that now the vectors embedding of the relationship are now the linear combination of three different components that are the clusters of the relationship, the actual relationship, and the sub relationship. As such, the loss function of the hierarchical relational structure is expressed as the linear combination, as reported here, of each group of the embeddings in the hierarchical structure of the relationship with possibly different weights. As for the loss function of the base model, it also requires a bit of change, because now we need to take into account that besides of the actual relationship, we also have clusters of relations that requires adding this summation here for considering the different relationship, each one in the corresponding clusters. And the last change was due to the fact that when we need to compute the score function of the base model, which is transr, now need to take into account that rather than the vector embedding of the relationship, we need to consider the linear combination of the vector embedding of the clusters of the relationship, the vector embedding of the actual relationship, and the vector embedding of the sub-relationship. We tested the developed models that has been dubbed transr owl HRS in order to assess the benefit of exploiting a more complex model enriched with a more fine-grained semantics of the relationship. And we compared the transr owl HRS with the base models that are those performing that registered the best performances in the previous experiments, that are transr owl and transr owl R, jointly with the base model, which is transr. We adopted the very same knowledge graph, link prediction and tribal classification tasks, and of course, standard metrics have been adopted for evaluating the performances. Here, it is important to make clear that we adopted for the experiment one of the variants suggested by Zhang and colleague, which is the top middle variant. That means that only the top and the middle layer of the hierarchy have been considered, and not the leaf level. This has been in order to keep under control the complexity of the model. And for clustering the relationship, the k-means algorithm has been adopted. And what we found out in our experiment is that the transr owl HRS was actually able to outperform the baseline models, particularly for the case in which we had missing axioms. That means for the case of NEL, But we had some nice surprises somehow. That means we found out some shortcoming, and the shortcoming occurred for the cases in which we had more comprehensive data sets. That was specifically the case of DBP, the 100 case, showing that the exploitation of a more complex hierarchical structure did not have significant value added when enough information is available, whilst it plays a role only when limited axioms are available. So we had interesting results, but somehow we need to put together these two different results, considering the characteristic of the knowledge graph that we should take into account. Now, given the lessons learned, the preliminary lessons learned when we tried to enhance existing numeric-based learning models with the background knowledge and the deductive reasoning capabilities that actually showed that we are able to improve the performances on knowledge graph refinement tasks. Let's move on the category of the symbol-based learning models, and let's try to understand if it makes sense to try to apply them to the existing knowledge graphs. Actually, several symbol-based learning methods have been developed, targeting different problems, for instance, concept learning, but also inductive instance retrieval. Here, I'm going to focus on a specific problem, which is learning disjointness axioms. What's the motivation for focusing on learning disjointness axiom? Actually, there are several motivations. The first one is that as it has been experimentally proved, disjointness axioms are often missing within ontologies. And the absence of disjointness axiom creates several problems. The first one is that noise can be introduced within our knowledge base. That means that we stay with a knowledge base which is consistent, but that is somehow wrong with respect to the domain of reference. That is mostly the meaning of these simple examples, in which we have three concepts that are journal paper and conference papers, both subconcept, subclass of the concept paper. And we have two assertions that are an instance in individual A is instance of the concept conference paper, but also of the concept author. And if we check for the consistency of this simple knowledge base, what we find out is that this knowledge base is actually consistent. But we know that in reality, an object which is a conference paper cannot be an author. And this is due to the fact that a disjointness axiom between author and conference paper is actually missing. Additionally, because of the absence of knowledge of disjointness axioms, we can also have counterintuitive results, which is what is showed in this simple example, in which again we have our journal paper and conference paper as a subconcept of the concept paper, and now we have just one instance of one assertion, which is the individual A is instance of the concept conference paper. When we try to apply deductive reasoning in order to assess if A is also instance of the concept journal paper, actually we cannot have any reply because of the open world assumption, because what happened is that we can actually build a model for A being an instance of the concept journal paper, and also we can find a model for A being an instance of the negation of the concept journal paper. So that's why the answer is unknown. And again, this is due to the fact that a disjoint transaction between journal paper and conference paper is missing, because we know that in reality, a journal paper is a different thing of a conference paper. The other point is that the absence of disjoint transaction is the main motivation for which it is so hard to collect negative examples, negative triples, that need to be used when applying numeric-based learning methods, knowledge graph embedding methods on the knowledge graph for performing knowledge refinement tasks. So if we are able to somehow complete the existing knowledge by adding disjoint transaction, we can both have a more fine-grained schema level information that is able to provide better insight of the data, and we can also have the main tool that allow us to collect negative examples that are extremely useful for applying knowledge graph embedding methods for performing knowledge graph refinement tasks. So what we try to do is to actually automatically capture these disjoint transactions by analyzing the data configuration. And the motivation why we try to do that is that we moved from the observation that the extension of disjoint concept actually is disjoint, so do not overlap. So the idea is to automatically capture disjoint transaction by looking at the data configuration and specifically by exploiting conceptual clustering methods. A conceptual clustering method is specifically a clustering method is an unsupervised inductive learning method that organizes a collection of unlabeled resources into meaningful clusters such that the intra-cluster similarity is high and the intercluster similarity is low. So given this collection of objects, ideally our clustering method should be able to discover these 40 different clusters. If our clustering method is also able to provide an intentional description for each cluster, then we will talk about conceptual clustering methods. The formal definition of the problem that we would like to solve is provided here, where given a knowledge base, where we both have the schema level information and assertional level information, and a set of individuals that could be even a small subset with respect to the whole bunches of the individuals in the knowledge base. The goal is to find n pairwise disjoint clusters, and for each cluster, we would also like to find a description DI that describes each of these clusters. Specifically, this description needs to satisfy the following constraints: that all the individuals that belong to the cluster that is that it describes are instances of the concept DI, while all the other individuals belonging to the other clusters different from CI, which is the cluster which is described by DI, are instances of the negation of the concept DI. These allow us to infer a disjoint transaction, to approximate the existence of a disjoint transaction between DI and all the other concept description describing the other clusters. In order to do that, we preliminary, so we need to make clear that other existing methods have been developed trying to learn disjoint transaction, but these have been mostly grounded on the exploitation of purely statistical based approaches without exploiting any background knowledge, and again without exploiting any reasoning capability. What we would like to do instead is to solve a clustering problem for learning disjoint transaction, and this is done by learning terminological cluster trees that are able to provide concept descriptions for each cluster. Specifically, a terminological cluster tree is a binary logical tree where a leaf node, each leaf node stands as a cluster of individuals, while each inner node, including the root of the tree, represent concept descriptions with respect to the signature, and particularly given an inner node, each departing edge, and specifically each departing edge in the left-hand side, represent positive examples for the concept description. Whilst for the case of examples following the left-hand side, the right-hand side departing edge, they represent a negative example for the concept description in the inner node. An example of terminological cluster tree is depicted here, where we have a terminological cluster tree describing the AI research community, and as you can see here, at each leaf node we find collection of clusters that are given by collection of individuals. Differently from the leaf node, we have inner node and the root node, and each one is represented by a description logic concept description. And individuals here in C1 stands for positive examples of this concept description, while individual in this cluster C2 stands for negative example of this concept description, and similarly for the other cases. Given a terminological cluster tree as the one that we have just seen in the figure, the way in which we obtain disjointness axiom is by adopting a two-step approach. In the first step, we build a concept set, which is obtained by traversing the tree in order to collect the description that describe the clusters that have been obtained at the leaf node. In the second step, given the concept set, we pick randomly two concept descriptions in the concept set, and if they are neither equivalent nor the one subsume the other, then we can generate the disjointness axiom between these two concept descriptions, let's say D and E, that are in the concept set, provided that this disjointness axiom has not been already generated. So given our example of terminological cluster tree, what we do is to first build the concept set by traversing the tree and obtaining the description of each clusters. And after the concept set has been obtained, we can pick two concept description within the concept set. Let's say the concept person and as publication and AI paper is one concept, which is this one, and the other one is this one, not person and proceedings, and it is quite straightforward to see that these two concepts are neither equivalent nor the one subsume the other or vice versa. So assuming that this disjointness axiom has not been already generated, we may generate the disjointness axiom between these two concept descriptions. The last thing that we need to know is how this terminological cluster tree can be obtained. And this is actually obtained by adopting a divide and conquer approach, where given the collection of individuals that are provided and general concept, generally we start with the top concept, the base case is given by testing the stop condition that consists in testing that the cohesion of the cluster exceed a given threshold. If the stop condition is not verified, then the recursive step is performed. This means that given a current node that contains that concept description, a number of refinement of the current nodes are generated. And these refinements are generated by using suitable refinement operators for description logic representation. Given this number of refinements, the best concept is selected and installed as a current node, where the best concept is the one showing the best cluster separation between the positive and the negative example. The last thing that we need to do is to move the examples, the initial set of examples here, along the positive and negative branches. And particularly, this is done by assigning to the left-hand side the individuals that have the smallest distance with respect to the representative element of the positive examples. That means that these will be positive examples as well. And the individuals that have the smallest distance with respect to the representative element of the negative examples will be moved towards the right-hand side. That means that they will represent negative examples. Of course, for collecting the set of positive and negative examples, the reasoner can be exploited. Another important aspect that need to be highlighted is that this solution does not require the number of clusters as an input parameter. Rather, it is able to actually find out the number of clusters by looking at the data distribution. We evaluated this developed method in two different testing two different aspects. The first one is to check if an axiom given a bunch of ontologies that have been taken into account, and these are ontologies that are publicly available. We just removed the one axiom, one disjointness axiom, and checked if the terminological cluster tree based method was able to rediscover the target axiom that has been removed. And we actually found out that the removed target axiom is has been always rediscovered. But we also found out that the method was able to actually learn additional axioms. So we also measured the number of additional axioms that are that have been always significant as a number, but we also checked if this high number of disjointness axiom could generate some inconsistency within the ontology. And we found out that actually a limited number of inconsistencies have been found. We also compared the method grounded on learning terminological cluster trees with respect to the methods that have been developed at the state of the art, which adopted a purely statistical approach. And in order to do that, we targeted a more complex problem, that is to rediscover a number of axioms that, that was equal to 20%, 50%, and 70% of the axioms in an existing ontologies that have been removed. Here, it is important to point out that given that the number of axioms that can be found within an ontology is quite often limited, we first generated additional disjointness axiom by adopting the strong disjointness assumption proposed by Stefan Schlobach and colleagues that mostly assert that given an ontology, two sibling concept in an assumption hierarchy need to be considered as being disjoint, and then we removed the 20%, the 50%, the 70% of the axiom, and we measured the rate of rediscovered target axiom, the cases of inconsistencies that could be generated by the methods, and also the number of additional discovered axiom. And what we found out again is that both the solution based on terminological cluster trees, but also the other solution grounded on the purely statistical approach are able to rediscover the removed axiom. And of course, the performance decreases where a larger fraction of the axioms are removed. That is the case of removing 70% of the axioms. But our method grounded on the exploitation of the terminological cluster trees outperformed the purely statistical based methods in terms of additional discovered actions. And this is due to the fact that whilst methods based on purely statistical approach can only learn disjointness axiom between concept names, the method grounded on terminological cluster trees are allowed to learn disjointness axiom that take into account also complex concept description, thus showing that actually the exploitation of the background knowledge and the reasoning capabilities actually may play a role in this regard. Here you can see some examples of disjointness axiom that have been discovered, and here there is an example of disjointness axiom that has not been discovered, and this was due to the fact that very few instances were available for both concepts, and this is the main motivation why the clustering process was not able to capture the disjointness between these two concepts. So to conclude, I showed a framework for enhancing existing knowledge graph embedding methods with the exploitation of background knowledge and reasoning capabilities. And I also showed that symbol-based learning methods can be particularly useful for supplementing schema-level information. And we can also use just a subset of the knowledge graph, and this may help the quality of the schema-level information which is already available within the knowledge graph. Particularly in both solutions, deductive reasoning capabilities have been also exploited, which are really important for the full usage of the background knowledge. There are many interesting research, additional research directions. First of all, a more in-depth study of the knowledge graph embedding methods enriched with the injection of background knowledge is needed, because we found out a way for solving the problem in presence of incompleteness, but then we lose something when we add more comprehensive knowledge graph. Still, scalability is improved, but need to be further studied, and we need to come up with the symbol-based solution that are actually can scale with larger and larger knowledge graph. A research direction that I consider very, very important is to complement knowledge graph embedding methods with solution for providing explanation. And we are working on that. We will present a preliminary idea on in the next few days at the Web Intelligence Conference. And another aspect that would be really interesting is to integrate additional approaches, reasoning approaches, such as the common sense reasoning when trying to learn both using symbol-based and numeric-based solution. This concludes my talk, but let me thank also colleagues and collaborators that worked with me in the development of the research that I've just presented here today, and they are Nicola Fanizzi, Nicola Flavio Quattraro, and Giuseppe Rizzo. Thank you.
Thanks a lot, Claudia. So we are a bit late, but we still will.